Hello, my name is Sean, and I'm joined by Katie, Matt, Sonia, and Sawyer from Team 7. We're here today to present our ME452 final presentation regarding our design project. So our product of interest that we're examining is pencil sharpeners. Specifically, we'll be examining an electric pencil sharpener. For standard electric pencil sharpeners, basic procedure is that the pencil will be pushed into contact with the blade, and the blade will be engaged while staying stationary. Here on the right is a quick glimpse of the pencil sharpener we're going to be examining. Next, we'll be examining our customer base. Our primary customer group will be students. This includes students from kindergarten up to university level. And then our secondary customer group is people who require assistance with stability, which includes the youth and the elderly population. And this secondary customer group was actually modified from our interim report. We expect our primary customer group to purchase in greater volume. So we expect about 60,000 units for the students and 30,000 units for our secondary group. Next, moving on, we analyzed the functions of our pencil sharpeners through creating a FAST diagram. We identified that the function of sharpening the utensil to be our primary function. And we cited that shape utensil and hold utensil are the primary functions for this diagram, while also placing an emphasis on the primary basic functions. Next, we moved on to the assembly sequence of our product. Sequence 1 here displays a assembly sequence that is made up of many smaller subassemblies, including the blade subassembly and the motor subassembly. Meanwhile, we created another subassembly sequence. Sequence 2 here utilizes fewer but larger subassemblies. And then moving on, we decided to compare the two using this comparison table. And then we decided that sequence 1 was stronger in all categories, but the ease of testing subassemblies because in sequence 2, there were less subassemblies to test. Next, we analyzed the success of our product compared to our functions using a function component mapping matrix. We've updated this from our interim, highlighted by the red text in our matrix. And as we went through designing our product, we used matrix to ensure that all of the components achieve a function and that all of the functions have an associated component.
For our bill of materials, the BOM shows that the total cost of the original pencil sharpener is $23.94, which is really relatively close to the retail price of $29.99. The calculated cost of that pencil sharpener is mostly due to the motor, which is $15.49 per unit. And if the motor price was significantly less, then the calculated cost would be a more reasonable estimate. For our functional component matrix quad chart, we have all of our parts to have a high functional importance, and only the motor, blade casing, and spring cover also have a high cost. For the product family design functionation differentiation, all of the functions identical for both customer groups cover the standard writing utensil functions, but the different functions for the secondary group is to be able to support hand stability, different utensil sizes, and control sharpening. And then for the platforms, all of our parts are a platform and only the main body is a module. This is because we will be able to change the main body to support our different functions for our secondary customers. For the component design, we have the different module being that main body. We have added a hole and also the selector stopper. Having that notch, we'll be able to stop our size selector, the different sizes for the different utensils, and we'll be adding additional piece so that we'll be able to change the size for different utensils. For the common interface, we will have the same interface for the original main body. It'll be able to have a snap fit attachment to the transparent container and the lower body. For the assembly sequence, our original assembly sequence was to add the main body before the transparent container, but this differentiates the products pretty early, a little bit early on. So by just changing that transparent container before the main body, we'll be able to save some time in the assembly sequence.
When designing for manual assembly, we decided to remove the fasteners that are part of the size adjuster and body interface. To do this, we added a flexible plastic shaft to the wheel that allows for a simulated snap fit and removes the fasteners. When designing for manual assembly, we redesigned the blade casing to fit the blade into a slot as opposed to inserting it and securing it with a fastener, as can be viewed on this slide. In designing for automated assembly, we eliminated a number of features rendered obsolete by the changes made to the blade insertion. Notches in the hole were removed from the blade, and on top of the blade casing, threads were added to make it able to be screwed on. The blade subassembly was deemed to have a high functionality and high cost. Its functions include engaging the sharpener, guiding the utensil, and supporting different sizes of utensils. After DFA, we eliminated fasteners, and all insertion is in the same direction. Before and after costs can be viewed on this slide. The critical dimensions for the blade and blade casing are the longest dimensions on each, 22 millimeters and 35 millimeters respectively. This is because the longest dimension of the blade allows it to support different size utensils, as is the longest dimension of the blade casing based on the function component mapping matrix. We recommend sheet metal working for the blade due to the thin nature of the blade and using stainless steel for added strength, and injection molding for the blade casing due to intricate shapes using polycarbonate.
Going into the design for manufacturing the size selector, some changes that were made were the removal of the clearance hole for the fastener, replacing the screw and nut with a flexible shaft, and adding a cap at the end of the shaft to lock it into place, which can be removed by squeezing it and pulling it out. So when conducting the DfM cost analysis on this modified version of the size adjustment wheel, it was found that it reduced the cost of the selector from 90 cents to 31. On the next slide, you can see a deeper look into the DfM cost calculations for the size selector in the before and after the redesign. So next, you can see the design for manufacturing of the blade. Some changes made here included the removal of the clearance hole for the fastener, as well as the removal of the edge slots, which allowed for the use of a standard punch, in addition to adding fillet edges to avoid sharp corners. The before and after costs can be found in the table below for the cost of 90,000 parts.
For our product service system, we decided to have a kind of sub function to allow customers to mail in their batteries, either if they've been expired or been depleted and need replenishing, and also to partner with local office supply store chains to facilitate the transaction if need be. This way they could either mail in or go to a store to make it easier. It benefits the consumer because they don't need to purchase a new battery unit at full price because we'd be offering it at a discount for doing a repeat customer service. And also batteries are guaranteed compatible. So this way the customer doesn't have to worry about, getting the wrong types of batteries or having batteries that are defunct in some way because the supplier would test them. And batteries will not be disposed in a harmful way to the environment. So this benefits the environment as well. So in conclusion, we believe that we've added an improvement to the existing product. We've added a module to be more inclusive to all age groups, the size selector. It's more cost efficient by about $1, a little over $1 for each unit. We eliminated fasteners. We did this through the blade casing and size selector, and the assembly is now in one direction. So for our critique, so the pros again are listed here. The cons are that we added a new screwing motion for the blade casing. We now have manual assembly for the size selector, and more precision is needed for the blade. And if we had to do the project again, we would have chosen a product that has more options to kind of improve it. It seemed like our product was pretty specialized or kind of polished as is for the functionality that it was designed for. And then also to kind of aid that, if the product had multiple functions, that would kind of give us more avenues to do more improvements on it as well. And different manufacturing processes being involved would also have enriched the experience, we think. Any questions?